Yesterday we started talking about Newton's law of universal gravitation, and essentially that law said and says that any two objects with mass exert a force of gravity on one another, an attractive force of gravity on one another. And that explains a whole lot for us, right? It explains why when I drop this board marker it falls towards the ground, because the board marker has mass, as does the Earth have mass. It explains why the Earth orbits around the sun, because there's a force, essentially a centripetal force, that keeps the Earth in orbit that is provided by this force of gravity. Why? Because the Earth has mass and the sun has mass. We can describe this force mathematically. Newton, although he didn't really know why this force existed between two objects with mass, he did know how to describe it really, really well mathematically. That equation looks like this. F with two absolute value signs around it, just like we put around the centripetal force equation. Means that force is a vector, but this equation isn't going to tell me what the direction is. It's just going to give me the magnitude. F is equal to big G. Okay, be careful, don't write it as little g. Little g is 9.81. This is not 9.81. It's equal to big G times m1 times m2. M1 and M2 are the two masses involved. It doesn't matter what order we put them in or which one is which. If we're talking about the Earth and the Sun, one of them is M1, one of them is M2, whichever. Okay, if we're talking about the board marker and the Earth, then one of them is M1 and one of them is M2. It doesn't matter which one is which. G times M1 times M2 over little r squared. We call this an inverse square relationship because F is inversely related to the square of r. Now, let's start identifying what some of these variables mean. This is my force of gravity. Technically, it's the magnitude of the force of gravity because it only gives me the value of it, not the direction. But you know what? That's okay. We know that gravity is always an attractive force, which means that two things that exert that force of gravity will always be pulled towards each other. It's the force of gravity, and it's measured in newtons. Okay? These are the two masses, whatever order you want to put them in, mass 1 and mass 2, and they're both measured in kilograms, as mass always is for us. R is the separation distance. It's not radius, it's separation distance. And when I say separation distance, I mean from the center of one object to the center of another. Now, that's measured in meters, and it can, I say it's not the radius, it can be the radius, but not always. Okay, if we're talking about the force of gravity that exists between you and the person next to you, then R would be the distance from the middle of you, from about your belly button, to that other person's belly button, from center to center. Okay, that's not a radius, because nobody's going in a circle here. But if we're talking about the force of gravity between the Earth and the Sun, the distance between the center of the moon and the center of the Earth, the center of the Earth and the center of the Sun, that is the radius, right? So R can be radius, but not necessarily. R is a distance that separates two objects, which also corresponds to a radius if the object is moving around in a circle. But only if the object is moving around in a circle. Going to be measured in meters. Remember to find that distance from the center of one object to the center of the other. Now, this last variable, G, this is the one that's going to be brand new to you. This is what we call the gravitational constant. That's a constant, a number. Just like 9.81 is a number, except that this is a constant that is the same anywhere in the universe. 9.81 changes, right? 9.81 on the top of Mount Everest, or little g is going to be different on the top of Mount Everest than it will be in Vancouver. But big G is the same at the top of Mount Everest as in Vancouver at the harbor side, as it is on Mars, as it is in some other galaxy. Big G is the same. Its value, big G, is 6.67 times 10 to the minus 11 Newton times meter squared per kilograms squared. Now the good news is this number, including the units, is on your data sheet, so you don't need to remember any of that. Just remember what it is. It's a constant, the same anywhere in the universe. That's what we call it, by the way, the law of universal gravitation, because this law, this equation, this variable, big G, is valid anywhere. It's anywhere in the universe. It's a universal constant. I want to do an example here. This is chapter 4 from your textbook. Chapter 4, because it says example 4.1, page 206. Mount Logan in the Yukon is 5,959 meters above sea level and is the highest peak in Canada. Earth's mass is 5.97 times 10 to the 24 kilograms, and Earth's equatorial radius is 6.38 times 10 to the 6. What's the difference in magnitude? Okay, let's not even worry about what we're being asked for right now. Let's set this question up. Here's the Earth. The equatorial radius of the Earth is 6.38 times 10 to the 6. So we're going to say this distance right here from the center of the Earth to the surface is 6.38 times 10 to the 6 meters. Does that make sense? I don't even know what I'm asked yet. I don't really care. All I care about right now is setting this up so I don't get confused later on when I do worry about what I'm looking for. All right, it says that the top of Mount Logan is 59 meters above that. So here's this mountain, Mount Logan. Okay, like it's kind of an odd-shaped Earth with an odd-shaped mountain there, but you get the picture. This distance above that surface of the Earth, of the top of Mount Logan, is 5,959 meters. Good? Okay, there's where we're at. We want to know the difference in magnitude of weight of a 55-kilogram person at the top of the mountain versus the base of the mountain. Now, this requires you to remember something from last unit. What is weight? What is weight? If I ask you to find weight, we talked about this earlier in this unit as well, actual weight, what is it? Is this person's weight 55 kilograms? No, that's mass. The person's weight is, in newtons, it's force of gravity, right? It's m times g, right? Don't write this down yet, okay? Jacob said it's m times g. He's absolutely right. The only problem with using this equation sometimes, and we've used it so far like a lot of times, right? But the only problem with using it is that we have to know what little g is. When you're on the surface of the Earth, we just say little g is 9.81. But the reality is it varies. From the base of Mount Logan to the top of Mount Logan, little g is slightly different. And we don't know what it is. If we know what little g is, then we can use that to find weight. But we don't know what little g is. It's something down here, and it's something slightly smaller up here. Does that make sense? All right. So what we're going to do to find the force of gravity, or the weight, is not use m times g this time, but rather we're going to use our new equation, which is gm1 m2 over r squared. So let's say at the bottom, or the base of the mountain, we're going to say the weight, or the force of gravity, is gm1 m2 over r squared. That's 6.67 times 10 to the minus 27 times mass 1, which is 55 kilograms. What's mass 2? Mass of the Earth, which on the back of your data sheet is 5.97 times 10 to the 24 kilograms. Divided by r squared. What's r? 6.38 times 10 to the 6th. No. At the base of the mountain, at the bottom of the mountain, that distance is this one right here. From the center of the Earth, from the middle to the surface of the Earth. Because that's where I am, right? Okay, in the end, r stands for the distance between the center of the two objects. The distance between the center of me and the center of the Earth is 6.38 times 10 to the 6. And then, of course, we square that. So let's do that on our calculator and get a number for that. We're not done the question once we get that, but we're halfway there at least, or just about halfway there. Let's say 6.67 times 10 to the negative, I said 27. It should be negative 11. What did I say before? I said 11 before? Yeah, it should be times 10 to the negative 11. No, 10 to the minus 11. I'm getting, sometimes so many numbers go through your head, you get numbers mixed up. I was mixing up there the mass of a proton with the gravitational constant, because the mass of a proton is 1.67 times 10 to the negative 27. So I just kind of combined two numbers there. All right, so 6.67 times 10 to the minus 11 times 55 times 5.97 times 10 to the 24. Let's get a number for that. That's the number on the top, the numerator. Now let's divide that by some brackets here. 6.38 times 10 to the 6. And we got to square that, right? Square that gives us 538. We're not done yet, so let's write the unrounded number, 538.0486. There's the weight or the force of gravity experienced by this 55 kilogram person at the bottom of Mount Logan. Now, would you expect that person's weight to be higher or lower at the top of Mount Logan? It's going to be lower. Gravity is going to be ever so slightly smaller at the top of Mount Logan, therefore the weight will be ever so slightly less. Let's calculate that value now at the top of Mount Logan. We're going to say g m1 m2 over r squared again. Sub our numbers in here. G is still 6.67 times 10 to the minus 11. M1 is still 55. M2 is still the mass of the Earth, 5.97 times 10 to the 24 kilograms. What's R going to be, though? Good. 6.38 times 10 to the 6 plus 5959. Why are we adding those two numbers together? Yeah, if I'm at the top of Mount Logan, I want the distance from the center of me to the center of the Earth. The center of the Earth from me is those two distances combined. So let's add those together, 6.38 times 10 to the 6 plus 5959. And then we've got to square that. All right, this is a little bit confusing here. We've subbed this into the calculator, so watch carefully. Just put down your pens and maybe do this with me on your calculator, okay? Let's get the number on the bottom first. 6.38 times 10 to the 6 plus 5959. Get that number, equals. Okay, there we go. Let's square it. Equals 4.07 times 10 to the 13. Now let's get the number on the top. 6.67 times 10 to the negative 11 times 55 times 5.97 times 10 to the 24. Divide it by that number we just got for the denominator, 4.07 times 10 to the 13. Gives me 537.0449. What was the question again? What's the difference in the magnitude of the weight of this person? The weight of the person at the top is 537. At the bottom, it's 538. Is there much difference? No, not much difference at all. But is it measurable? Yeah, absolutely it is. We want to find the difference. All we got to do is subtract these, right? This is grade 1 math now. We're going to say that number minus 538.0486 gives me, actually I should have subtracted the bigger minus the smaller, right? So the difference is, let's say, I'll call it delta F is, I think it was just 1.00, yeah. So there's 1 Newton difference in weight. That's a small difference, but you know, when you're comparing it to 537 newtons, it's measurable. With precise enough equipment, that difference in weight is measurable. Your mass stays the same, but your weight, which is your force of gravity, changes because you're further away from what's causing it. You're further away from the middle of that thing that's denting the fabric of space-time. And if you remember yesterday, at the risk of making this longer than I want it to be, when you're further away, look, this is the middle of the Earth down here. Okay, I'm right here. I'm up here. Okay, the slope here isn't as much as the slope down here, right? So as you get further away from the center of what's causing that dent in the fabric of space-time, which is the Earth, then gravity is going to get weaker. It's like tobogganing on that hill on a not very steep part at the top, but then it gets steeper as you get closer to the bottom. Okay? Yep?
What the difference with delta H?
So look at these two questions, please, on page 207. I want to do number 2 right now. It says the mass of the Titanic was 4.6 times 10 to the 7 kilograms. Yeah, it's not now. Suppose the magnitude of the force exerted by the Titanic on that fatal iceberg was 61 newtons. You guys know the story of the Titanic, right? Okay, it's maiden voyage, this unsinkable ship traveling in the North Atlantic. Captain's had a few too many beers and isn't paying attention to all the iceberg warnings that have been put out for some time, and all of a sudden they smash into this iceberg and the ship goes down. This unsinkable ship on its maiden voyage goes down. Anyways, takes like 1,500 people, something like that, with it. There was this iceberg and this ship were both so big that there is a force of gravity that is quite measurable. 61 newtons that acts between them. That's a big force of gravity when we're talking about two objects on Earth, right? Like, that's a big force. Separation distance 100 meters. What was the mass of the iceberg? We're going to say here for this, F is equal to G m1 m2 over r squared. And we're going to solve for either m1 or m2. It doesn't really matter which one you're solving for, right? Same thing. What do you got to get rid of? Well, everything, right? G, m1, and r squared. How do you get rid of the r squared? Yeah, it's m2 divided by r squared, so we're going to take it over to the other side by multiplying. F times r squared is equal to G times m1 times m2. Still solving for m2. How are we going to get rid of the G and the m1? What are we going to do? Yeah, we're multiplying m2 by G and m1, so we're going to divide both sides by that to get the value of m2. F times r squared over G times m1 equals m2. Now, we sub our numbers in here, right? We have all these values. This becomes pretty straightforward now. We have F, we have r, it's 100, but then we got to square it. And we have G is 6.67 times 10 to the minus 11. And we have the value of m1, which is 4.6 times 10 to the 7. Be careful on the bottom here, okay? Use some brackets. Here, let's just do this, actually. Remember what we've always said? When you end up with some calculation on the bottom, do it first. So let's multiply G, which is 6.67 times 10 to the minus 11, times m1, which is 4.6 times 10 to the 7 kilograms. Okay, there's the bottom. There's the bottom number. Now let's multiply the top numbers together. Here, the force is 61 times r squared is 100 squared. And let's divide that by the number that we had on the bottom, 0.0306. Gives us the value of m2, which is 1.988 times 10 to the 8 kilograms. Look at that. We got to express this in 2 digits, right? 2 digits. Look at the third digit. This is a good one. Third digit is 8. What do? Round up. But wait a second. The next one is a 9. So we got to round 19 up to 20, right? It becomes 2.0 times 10 to the 8 kilograms. So pretty heavy iceberg, right? What do they say? Something like 90% of an iceberg is underwater? Is it 10% above? Yeah. So even, you say like, oh, I didn't see the iceberg, I swear. Well, the amount that was above, okay, the amount that was above, like, is still 10% of this, which is a pretty high value, right? 10% of this is still 1.9 or 2.0 times 10 to the 7 kilograms, right? Make sense? So there's still an awful lot of that iceberg that's above the surface.